my screen?
Yes. So, hi everyone. Welcome to the 35th session of our MedAI group exchange sessions. And this week we have our own Siyi Tang from Stanford here with us to present her research on self-supervised graph neural networks for EEG seizure analysis. As you might all already know, Siyi is a PhD student here in the electrical engineering department at Stanford, advised by our professor, Daniel Rubin. Her research aims to leverage the structure in medical data to develop better medical machine learning models and enable novel scientific discovery. She's also interested in enhancing the human interpretability and clinical utility of medical ML algorithms. So thanks so much, Siyi, for presenting your work today. And how would you like questions for today?
Yeah, feel free to interrupt me at any time.
Awesome. Okay, so let's try to make this session as interactive as possible. And without further ado, let me hand it over to Siyi.
All right, thanks Nandita, and thanks everyone for joining us today. So today I'm going to present our recent work on self-supervised graph neural networks for EEG seizure analysis. This paper has been accepted to ICLR 2022, and you can access it through the QR code here. So why are we interested in graph neural networks and self-supervision for EEG-based seizure analysis? Let me briefly introduce background about EEG here. So EEGs are brain electrical activities recorded from electrodes placed on a patient's scalp. It is an important test for seizure detection and classification. By seizure detection, I mean is to identify if an EEG has a seizure or not. And seizure classification is to classify the seizure into finer-grained seizure types, such as focal versus generalized seizures. So traditionally, EEG-based seizure detection and classification requires a trained EEG reader to manually analyze EEGs that can range from hours to days. So this is a very expensive and time-consuming process. Recently, machine learning, in particular deep learning, has been used to develop automated seizure detection algorithms. Based on these two survey papers in 2020 and 2021, we can see that convolutional neural networks, or CNNs, are the most frequently used network architectures. We also found some papers about graph neural networks applied for seizure detection. If we look at seizure classification studies, there are much fewer studies. And this is most likely because seizure classification is a much more challenging problem. And there is very limited number of public data sets that have seizure type labels. Nevertheless, we still found that CNNs still dominate prior seizure classification studies. And to our knowledge, we didn't find any study that have applied graph neural networks for seizure classification. However, there are some limitations of prior studies. So first of all, most of them use convolutional neural networks. However, as we have seen in the previous slide, EEGs are recorded by electrodes placed on a person's scalp. So it is the scalp is like a manifold rather than a 2D flat surface. Therefore, EEG signals have an inherent graph structure. But CNNs assume Euclidean structure in EEGs, so this ignores the natural geometry of EEG sensors and the connectivity in the brain networks. And second, most studies use traditional supervised learning approaches. However, certain seizure types are rare by nature. So supervised training requires both data and labels, but it might not be optimal, or it might be challenging to get high performance on rare seizure types. And lastly, all prior studies lack a quantitative model interpretability approach or analysis. So some of the prior studies have shown qualitative heat maps or saliency maps for interpretability, but they did not measure the model interpretability quantitatively. In order to address these limitations, we propose a graph-based modeling approach instead of CNNs, as well as a self-supervised pretraining approach to improve the model performance, particularly on rare seizure types. We also propose quantitative metrics to measure the model's ability to localize seizures. All right, so before I go into details about the model architectures, let me define what we mean by seizure detection and classification in our study. We formulate the seizure detection problem as a binary classification of seizure versus non-seizure, given 12-second or 60-second EEG clip or EEG window. So the 12-second and 60-second windows are driven or inspired by EEG domain knowledge. EEG readers usually read EEGs in a 10-second window. So 12-second seizure detection can be considered as fast detection, whereas 60-second EEG seizure detection is considered slow detection because the model sees more signals. And for seizure classification, it is a multi-class classification of the fine-grained seizure types given a 12-second or 60-second EEG clip. And this figure shows an overview of our methods. I will go into details later, but the top left figure shows the 3D view of and the bird view of the EEG electrodes, the most commonly used EEG electrodes. And figure B and C show the example EEG graphs defined by our methods. And the bottom figure shows the model architecture. So how do we construct EEG graph? Remember that this is like the bird view of the EEG electrodes. And so we propose two different ways of constructing EEG graphs. The first is, we call it distance-based graph, where the edge weight between node I and J. Yeah, so in the graph, each node is one EEG channel or one EEG electrode. And the edge weight between node I and J, denoted as Wij here, is based on the physical distance between electrodes I and J defined in the 1020 standard system using this thresholded Gaussian kernel. So this method captures the natural geometry of EEG sensors, and it results in a universal undirected weighted graph as shown here. In fact, this graph looks like EEG montage used clinically. I believe it's called longitudinal bipolar and transverse bipolar EEG montage. And the second method is based on the cross correlation between the signals in EEG channel I and J.
See, what do you mean by universal in the first case?
Yeah, in universal, it means for each EEG clip or each EEG input, the graph is the same across all the inputs.
Okay, thank you.
Yeah, yeah, and the second approach, cross-correlation based approach, actually captures the underlying brain connectivity. So cross-correlation can be think of like a proxy of the functional connectivity within the brain networks. And to introduce graph subacity, we only keep the top K neighbors of each node. And for this method, it results in a unique directed weighted graph for each EEG clip. So you can think of each EEG input has one unique graph.
I have a quick question about the distance-based graph C.
Right.
So is the distance that you said based on a standard, does it take head sizes into account while deriving the distance between electrodes? Like I can imagine an infant versus an adult is probably going to have very different distance.
Yeah, that's a good question. No, we didn't. So we only use the standard system, which could be problematic. Like what we said, different people have different size, that their scalp is different. Yeah. But in general or experimentally, we found that it's a good proxy for across all the patients.
I see. Got it. Thanks.
See, what is your sigma in your distance-based graph formula? I thought that you are using some normalization parameter there, no?
Where's the the sigma is we just use the standard deviation of the distances.
Ah, okay.
Yeah, but it could also be like a hyperparameter as like a yeah.
Okay. Yeah. So I was thinking you did that, like that's why I didn't ask.
Oh no. Yeah. For the graph neural network, we extend this model called diffusion convolutional recurrent neural network to model EEGs. So the spatial dependency is modeled by diffusion convolutions on the graphs. And so basically what diffusion convolution is, it models the graph or like, the diffusion process as like random walks on the graphs. And the W and D here, the D is, I believe is the diagonal matrix of the graph, and W is the adjacency matrix of the graph. And for temporal dependency, it is modeled by gated recurrent units, a type of recurrent neural network. And in order to simultaneously model the spatial and temporal dependency in EEG signals, we replace the matrix multiplications in GRU with the diffusion convolutions. And finally, in order to produce predictions for seizure or seizure types, we stack several layers of the diffusion convolutional recurrent layers, followed by prediction layer or fully connected layers. We also propose a self-supervised pretraining strategy, which is to pretrain the DCRN or the graph model for predicting the preprocessed EEGs for the next time period, given a previous EEG clip. So you might have seen this method called forecasting or next time period prediction. And it is, the model has an encoder-decoder or sequence-to-sequence architecture, where the encoder and decoder have several stacked diffusion convolution recurrent layers. For model interpretability, we use a simple occlusion-based method. So we occlude 1 second EEG in one channel at a time and compute the relative changes in the model outputs. And then we normalize the relative changes so that we get a normalized occlusion map. And to quantitatively measure the model's ability to localize seizures, we define two metrics called coverage and localization. And for this definition, we need actually ground truths per channel seizure annotations, which is provided by the dataset we use. So for coverage, it measures how many true seizure regions are detected, which is analogous to recall in binary classification. And for localization, it measures how many true seizure regions or how many detected seizure regions are true seizure regions. And it is analogous to precision in binary classification problem. So before I move on, is there any question?
So the coverage and the localization are measured per data set, like it's a single value for the entire data set?
No, it's a measure per input per EEG clip.
I see. So given a single EEG clip, you find out like how much, if it was a seizure, then how much, like what fraction of the seizure was a true seizure, and I see. Got it.
Yeah, exactly. Mm. All right. So in our study, we use this public Temple University Hospital EEG seizure corpus. It is one of the, or I believe it's the largest public EEG seizure data set to date. It has around 50,000 EEGs or 5,000 EEGs, 3,000 annotated seizures, and 8 seizure types in total. And before we move on to the experiments, we actually refine the seizure types in the data set. So specifically, simple partial and complex partial seizures, which are two of the seizure types in this data set, they are both focal seizures characterized by a clinical behavior, whether the patient is conscious during the seizure or not. So these seizures are not always distinguishable using EEGs alone. Clinically, the patients are usually also monitored by videos or video recordings. So such clinical behaviors can be seen on the videos. However, if we want to use EEG alone for the seizure detection or seizure classification, it is not very reasonable to actually try to distinguish these two seizure types. So here we merge simple partial, complex partial, and focal non-specific seizures into a combined focal seizure class. And also tonic and tonic-clonic seizures are very rare in the data set. In order to maximize the training size, we merged these two seizures because they always start with a tonic phase. So the beginning of tonic and tonic-clonic seizures are basically the same. And we also exclude myoclonic seizures because there are only two such seizures in the data set. So we ended up with 4 seizure types in total: combined focal, generalized non-specific absence, and combined tonic seizures. And as you can see here, these 4 classes are still very, very imbalanced, where the combined focal seizure is the largest class, and absence seizure and combined tonic seizures are the smallest classes.
Quick question.
Mm-hmm.
So is it the case that if like an EEG clip, if it's focal, it cannot be a combined tonic? Like, are they mutually exclusive, or can there be multiple seizure types occurring within a 12-second or a 60-second window?
Yeah, that's a good point. For seizure classification, we purposely preprocess the EEG clip so that there are no, there is only one seizure type.
I see.
EEG clip.
Okay.
Yeah, but for seizure detection, it doesn't really matter. It's
Mm-hmm.
just to a binary classification. Yeah, so for preprocessing, we slide the 12-second or 60-second non-overlapping window over the long EEG signals to obtain EEG clips. And we also transform the raw EEG signals using fast-forward transform and only kept the log amplitude of the positive frequency components. And this preprocessing method has been pretty commonly used in prior studies as well. All right, yeah, so now let me show you some results. This table here shows the DCRNN performance, or our graph model performance, without self-supervised pre-training compared to 3 baselines. The dense CNN and CNN LSTM are from prior studies, and LSTM has also been widely used in prior studies. So we can see that DCRNN outperform the other baselines on both seizure detection and classification. And we also compare our results to the reported results of 2 prior studies. These 2 studies both used TUSG as their in their data set. So in order to compare to the Asif et al. 2020 paper, we actually performed 7-class seizure classification using their 3-fold patient-wide speeds. And we can still see that our model outperforms. Yeah, most of our models outperform the previous studies. And the bottom 2 rows show the model performance with self-supervised pre-training. We can see that self-supervised pre-training substantially improved the DCRNN performance, which validates our hypothesis that self-supervised pre-training can help improve the performance of the models. And here shows the ROC curves and the confusion matrices. So one particular observation is that if we look at the bottom right corner, we'll see that self-supervised pre-training actually greatly improves the classification accuracy of the combined tonic seizure, which is one of the smallest or rarest seizure types in our data set. Yeah, and remember we performed occlusion-based model interpretability analysis. So we can actually visualize the occlusion maps as heat maps overlaid on the raw EEG signals as well as the graphs. And the top row shows heat maps for 2 focal seizures, and the bottom row shows heat maps for 2 generalized seizures. For those of you who are not familiar with EEG or seizure, focal seizures means the seizure or focal seizures always start from like one hemisphere or one region of the brain, whereas generalized seizures always start from both hemispheres of the brain. So if we look at the top row, we can see that, so in this analysis, we actually asked a board certified neurologist, Chris, to analyze the EEGs and the heat maps and tell us if the heat maps make sense or not. So on the top row, we can see that the highlighted regions actually correspond nicely with the more abnormal EEG channels. Whereas in the bottom rows, we can see that the highlighted regions are more diffused across the channels, which makes sense for generalized seizures because generalized seizures usually start in both hemispheres.
Could you explain how, like if I remember correctly, you used an occlusion-based technique, right? So you occluded 1 second of every channel.
Yep.
Probably I missed this point. Like, how did you encode the EEG signals here?
Sorry, what do you mean? How do I?
Yeah, so the EEG signals are one-dimensional signal data, right?
No, it's multi-channel. So we have 19 channels in total.
Okay, and for each channel, do you use any kind of like encoding principle or no?
For each channel, we just did preprocessing using fast
Okay.
Fourier transform. Yeah.
So you are using the full temporal data.
Yes, full temporal over 12 seconds or 60
12
seconds.
seconds. Okay.
Yeah.
Okay.
Yeah. So this is the distribution because coverage and localization scores are computed over or for each EEG clip. So we can plot the distribution of these 2 scores. And we have several observations from the results here. First, we can see that DCRNNs have more high coverage and high localization scores compared to CNN or dense CNN in this case. And if we look at distribution of scores that are above 0.9, we can see that DCRNN has much more of the high scores compared to CNN. And we also observe that self-supervised pre-training improves coverage and localization scores. And correlation-based graph actually results in higher localization scores compared to distance-based graph. And here shows 2 example heat maps with localization score above 0.9. So we can see that, and the red boxes are the ground truth seizure annotations. So we can see that the highlighted regions overlap pretty well with the annotated seizure regions. So this again like suggests that, this makes sense because the localization score is pretty high. Yeah, is there any question here before I move on to more discussions?
Because the only one thing is kind of strange to me, see, like when you show the heat maps, because if you analyze like the discrete values in those signals, like it seems that they are analyzing it in a continuous manner, right? Like you see, like the emphasis was given on the full signal data, not on some portion of the signal data. So I don't know what is the reason for that.
Sorry, you mean this figure in particular?
Yeah.
You mean the heat map is not?
Yeah, the heat map.
Yeah. So yeah, we actually didn't show the heat map for values below 0.5.
Ah, okay.
Yeah, yeah.
Okay.
Yeah.
Okay.
Yeah, so in conclusion, we propose a graph-based modeling approach for EEG-based seizure detection and classification. And we developed two graph structures, distance-based and correlation-based graphs. The distance-based graph captures the natural geometry of EEG sensors, whereas the correlation-based graph captures the brain connectivity, and it actually better localizes seizures than the distance-based graph. We also propose a self-supervised pretraining strategy, which improves the GNN performance on both tasks. And it actually sets a new state of the art on the public data set. It also improves the classification of rare stereotypes and provides better ability to localize seizures. So moving forward, there are actually many exciting directions to explore. First, our proposed EEG graphs are defined using domain knowledge rather than learned from the data. So in the future, we could explore dynamically learning the graph structure within the model itself. And also EEG signals are very long. Although we use 12 seconds and 60 seconds in our study, longer EEG signals could be used, which would potentially provide more temporal information there. However, if for long sequences, we need a model that can capture long-term temporal dependencies. So recently, some models called state space models, based on state space, have been developed. So from one of the lab in Stanford. So I think that's a very promising approach for future work. And finally, the extension of current methods to a more generic graph model for all kinds of multivariate time series will be interesting as well. All right, yeah, that's it. Thanks for listening, and feel free to reach out to me if you have any questions. And let me stop here for questions.
Thanks so much, Siyi. I think that was a great talk. Yeah, let's open up the floor for questions. I can start off with one if, I think.
Yeah, hi, sorry.
Go ahead, yeah.
So I'm a medical student at Emory who's going into neurology and just participating in this as part of a machine learning elective. So a lot of the mathematics is over my head, but I'm very fascinated by the clinical implications. I was wondering, in the data set that you used, you might have said this at the beginning, so apologies, but were all of the seizures, the seizure types classified before you ran any of the analysis? So, for each seizure that's in the data set, does it say that it's a focal, complex, tonic-clonic? And then that is something that gets encoded in your machine learning algorithm?
Yeah, so we use these seizure types as, so the data set has labels for these seizure types. It basically indicates the start and stop point of the seizure. And so that's why we can use it as a label for each EEG clip. And we know within this EEG clip, whether there is focal seizure or generalized non-specific seizures, etc.
So would some future work also involve EEG clips that don't have a label. So I'm thinking if this could happen, if this kind of classification could happen in real time.
Oh, yeah. So ideally, if the model is well trained on like the training data, then it should predict an EEG without any labels, just to predict what seizure type this EEG has.
Cool. Great. Thank you.
Thanks.
I have a question as well, Siyi. So in the end, you saw that the correlation-based graph produced better results than the distance-based graph. I was wondering if you tried or plan to try like just a weighted combination of the two scores in order to weight your edges. Like that way you can get the benefit of both the distance-based as well as the correlation-based scores.
Yeah, that's a good idea. Yeah, I believe we could do that, and also some other methods to construct the edges, especially using like neurology domain knowledge would be also pretty interesting.
Are there any other questions?
See, did you compare like the number of edges between the correlation versus the distance-based graph? Is the number of edges the same or is it changing?
We didn't really compare it. But for the correlation-based graph, it's always changing depending on.
Right.
Sorry. Yeah. It's for the correlation-based graph is to change depending on the data.
Right.
Yeah, we didn't really compare it.
Okay, because I would imagine like your correlation-based graph probably gives you better performance because it's more like specific to that particular case or something like that, right? Because
yeah. So it's more like because it's derived from the data itself. So
right.
That might be one of the reasons.
Okay. So you didn't do like the change in the number of edges and see if it has any performance on the final predictive analytic performance, right?
No, we didn't do that.
Okay.
I remember one of your previous experiments, like you had arbitrarily swapped like the electrodes to see whether it like the model can capture something like that. Like were there some augmentations like this that you performed for this work as well?
Yeah, that's a good point. I didn't include it in this presentation, but we did perform augmentation during training. Basically we randomly swap 2 electrodes along the midline, and as well as randomly scaling the magnitude of the EEG signals. Yeah.
So it actually improve your performance, right? It doesn't have any kind of like drop in performance, because I think that would be another like interesting ablation study too, just to see that after swapping, if your model were able to predict.
Yeah. Let's actually I think that could be also used as like a self-supervised pretraining methods, just to randomly swap 2 electrodes and predict whether any electrodes swapped, things like that.
Oh, and also I think Iman, so I think there are specific swaps that are allowed, which are good for the model, and then for my work on out of distribution work, I actually randomly swapped in the bad pairs in order to get like things that are adversarial or like incorrect. So
so this kind of like similar concept holds also for ECGs. So you can imagine like 12 leads, right? So some of the leads can be swapped, some of the leads cannot be swapped.
Mm-hmm.
And it's the same similar concept, like how you want to correlate the information coming from different leads. So I think if you are interested, you can directly take the model that you train for EEG and try it on the other ECG data.
Mm-hmm. Yeah, that would be interesting.
Yeah, because they also have the similar connections. You can imagine like
Mm-hmm.
the closeness
Yeah.
connections, like the signal correlation based connection.
Mm-hmm.
Raman, you can speak up.
Yeah, so just as you were mentioning, we're seeing in the metrics you have coverage, localization, but how does let's say, the magnitude of the signal that it's being measured affect the model's ability to detect the seizure? Because you mentioned that you were playing around with those values for augmentation, right?
Yeah, we didn't really do ablation study on that. I guess, yeah, because the augmentation is mainly just to diversify the training data and reduce overfitting. Yeah, but I think that's an interesting ablation study to do. And also for this for these two metrics, actually we have to normalize or scale the occlusion values to be between 0 and 1. And we just set a cutoff point at 0.5. So occlusion value above 0.5 means like high, highly detected seizure region, so that we can compute this coverage and localization metrics.
Okay, I see. Thank you.
Could you explain this occlusion based a little more? Actually, after Ramon's question, I'm I thought maybe I understood incorrectly. So for your 19 channel, let's say 60-second clip, you take each second, like a window of each second for every channel, for every clip, and then you zero it out, or what do you do in order to prevent?
Yeah, we just zero it out.
I see. And then see what the change in prediction is in your model.
Yes.
I see. And the change in prediction is in the actual raw values of the scores, or is it like in the case of seizure classification, whether the class changes or
yeah, it's just the output logics, I believe. Yeah.
I see. Got it. Okay.
Yeah, this is just a simple occlusion method. I believe like other more advanced methods can be used to more accurately capture the interpretability. Yeah. Any other questions?
Yes. Just a quick one on the self-supervised pre-training section. How good was the pre-training have to be for you to actually use that trained section of the model?
How good? I think I just trained it for until it converges like the validation loss plateaus.
Okay, so you didn't necessarily have to, like, let's say, get the best performing model for that task in order to use on the downstream, or?
Yeah, we did. I believe we did some like hyperparameter tuning for this self-supervised pre-training as well, just to get lower validation loss. And then we use the trained or pre-trained model weights to initialize our downstream models.
Because I think it's a very challenging task given the smaller data set, like you achieve this high performance. Yeah. I think then probably pre-training plays a big role.
Yes, exactly. Yeah. So I think the model actually learns quite a lot of signals from the pre-training just to predict the next time period.
And is the seizure detection versus the seizure classification, are they on the same patient set, or are they two different data sets in the Temple?
They are same patient sets, same trend validation test sets. Yeah.
I see. Okay. So you just need to fine tune it once, like you don't need to fine tune it separately for.
Oh yeah, yeah. So we use the same pre-trained model for both tasks.
Awesome. So are there any other questions for Siyi? I guess if not, then let's thank Siyi with a round of virtual applause. And thanks so much, Siyi. And feel free to get in touch with her for more questions or follow-up work. And we'll have the talk up on our YouTube channel by tonight, and feel free to take a look as well. So we'll see you next week with another speaker at the same time. So thanks, everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye-bye.